All right. Few more exercise problems, and including the explanation for the previous one. So let's bring that up. And where did it go? All right. Build out model. Chapter 1. Right. So I was talking about this last class, and then I had the solution, I had my notes. It turns out it was correct. I was just needlessly confusing myself. So we had the circuit, we had a Zener diode. As a recap, let's go to the top. We had a diode circuit with D1, right? D1 is a regular diode, D2 is a Zener diode. Value for VZ is 5 volts. R1 and R2 are 1 kilo ohms. We were asked to analyze the circuit using the ideal diode model and determine V out over V in, the transfer characteristic. How is the V out changing as a function of V in? And so we went through the positive half cycle. Doesn't matter what values we have in the positive half cycle, whatever you give as V in, we would receive at the output. And so the output characteristic was a linear plot, linear line at 45 degrees in the positive half cycle. In the negative half cycle, it was still the same because the Zener diode would remain open. So if the Zener diode remains open because it's non-conducting, right, until it reaches its Zener voltage, it remains open. So the circuit still behaves as, and we obtain V out is equal to V in. But now, when V in crosses or increases higher than the Zener voltage, the Zener diode turns on. The Zener diode turns on, it behaves as a voltage source of plus 5 volts. Right? Behaves as a voltage source of plus 5 volts. It holds the voltage constant at 5 volts. So instead of, and we can analyze this by taking Zener diode as positive at the anode or positive at the cathode. Remember, when you first introduced the topic, we stated that Zener voltage or Zener diodes always work in reverse bias. So we always take the positive reference at the cathode, and that is still true. In this case, it doesn't matter. Actually, in all cases, it doesn't matter what you take as the reference. Okay, and so that's what tripped me up last class. So instead of taking plus at the top and minus at the bottom, let me take the usual convention, and cathode should be positive for Zener diode because it's working in reverse bias, right? So let's say it's applying a voltage source of 5 volts with this polarity. Does that make sense? Right? And in any case, circuit analysis, the first rule is it doesn't really matter what direction of current you take, assume, or what polarity of voltage you assume. If you go through the solutions, your answer will turn out to be the same. And so if you take with this polarity, or if you flip the polarity, your answer will be the same. It will not change. And I can show that to you. So here, this gets flipped, right? To the minus and plus. So now if we look at R1 and R2, and I redraw the circuit, what do R1 and R2 see? They see V in and they see VZ applied in series. R1 and R2 applied in series. Okay. So now it's applied in series, and let's say V in is 6 volts. Okay, let's say V in is 6 volts. So what is the total voltage being applied to R1 and R2? Vin plus Vz, right? 11 volts. So then 11 volts is applied to series combination. The resistor values are equal. What is the voltage drop across R2? 5.5, right? 5.5. So voltage drop across R2, and this is going to get messy. This is like scratch work. Or V in is equal to 6 volts. Total resistor voltages is equal to 6 plus 5 is equal to 11 volts. Therefore, VR2 be 11 times R2 or R1 plus R2 is equal to 5.5 volts. 5.5. Okay, 5.5 volts. Now, if VR2 is 5.5, and then let me just draw it here. This time I'm going to do V out. V out is being applied, not applied, is being measured across this. This is VR2. Did I apply it correctly? My circuit. For this case was 11 volts. So 5.5 and then minus 6 volts, 5 volts. This should be 5.5. Again, I am. Yeah, my answer is 5.5 in this case. Plus minus 5.5. So V out is taken across the resistor and the Zener diode. Sorry, again, this was the case. We took anode as the positive, cathode as the positive reference, right? So now my V out is, what is my V out? 0.5, right? V out is 0.5. So for all cases above 5 volts, it increases by 0.5. Okay, increases by 0.5. Below 5 volts, the diode is off, so it doesn't matter. V out is equal to V in, and hence we have a linear line, which is this portion, right? That's portion. And above, for every 1 volt you apply, or every 1 unit voltage you apply, the output's going to be half. 5 volts will always be consumed by the Zener diode. Okay. Zener diode will hold 5 volts constant across it, always consumes 5 volts. So output will always be half of what you apply as the input. And that's why we get a slope of minus 0.5. Okay. All right, before I forget, Friday quiz today started earlier a few hours ago. Only thing that's different is instead of the deadline being midnight tonight, I gave it until tomorrow. So students can begin from today until all the way till tomorrow, Saturday night. Okay. So Friday, this is the last Friday quiz of the quarter. And then next Monday, we will have the last Monday quiz. And I'll post an announcement regarding that, but it'll be on sequential logic design. Okay. So now let's do a couple of exercises where, and these are interesting circuits. So you can take a look and you can tell me would these circuits behave. So all right, so we have a circuit which has two diodes. A straightforward circuit. Then connected to a resistor. The resistor is connected to ground. And you're taking V out across that resistor. And we have two inputs being applied to that circuit. Conditions are ideal diode analysis. Okay, we're using ideal diodes. And VA and VB can be either 0 volts or 5 volts. Okay. 0 volts or 5 volts. And determine VO for all combinations of VA and VB. These are diodes D1 and D2. So how many possible input combinations can we have? Four. So let's see. If VA, VB is 0 volts and 0 volts, what will the circuit look like? So ideal diode analysis, as a reminder or a recap, we have an anode and a cathode. Ideal diode analysis, we simply have to look and observe whether the anode is at a higher potential than the cathode. If the anode is higher than the cathode, diode is on. If the anode is the same as the cathode or less than the cathode, diode is off. Okay, meaning forward bias. So the only condition for forward bias is it must be slightly larger. It could be 0 and 1 volt. It could be 0 and 5 volts. It could be 0 and 10 volts. It could be 5 volts and 10 volts. But as long as the anode is higher or larger voltage, it could be 0 and 0.1 volts or 0.01 volts, doesn't really matter. Ideal diode model simply means, in theory, As long as the anode is higher voltage, it's on. So based on that condition, if VA and VB are both 0 volts, then by show of hands, is diode 1 off? Show of hands for diode 1 on. One off. Okay, show of hands. Diode 1, D1. Is it on? Is it off? D1 is off. How about D2? Show of hands if it's on. Show of hands if it's off. D2 is off. And if that is off, how does my circuit look? How does the circuit appear? Simply the resistors, because they're replaced with an open circuit. So what is VO? VO is 0 volts. Let's take a pause, think over that. Let me know if you have any questions. Right, all for ideal diode analysis, all we need to look at is the relative voltage of the anode with respect to the cathode. The anode is higher, diode is on, and replaced with a short circuit. If diode is off, then if anode is the same or lower than the cathode, then diode is off, replaced with an open circuit. And then you just redraw the circuit according to your assumptions, and then determine what the output is. So let's look at VA and VB as 0 volts and 5 volts. Write it down and let me know what the state is. So VA, the anode is connected to 0 volts. So diode D1 remains off because it's connected to 0 volts. How about D2? D2 would be on indeed. So D1 anode is connected to 0 volts, so off. Anode goes 5 volts, then it's higher than the other end, turns on. So if it turns on, what is my output? Let's redraw the circuit. So for this possible state, D1 is off, so it stays there. This is connected, but it doesn't actually matter. Then 5 volts VB can be written as or shown as this voltage source. So now what is VO? 5 volts. It always helps me to redraw the circuit so I can better visualize it. So that's something I also encourage students to do. Okay. So then combination of VA and VB as 5 volts and 0 volts. Right? Whichever diode is connected to 5 volts is going to be on. So in this case, D1 is on, D2 is off. It doesn't change V out because V out remains at 5 volts. Okay. And the last condition, VA and VB are both connected to 5 volts, meaning both diodes are on, and therefore V out stays at 5 volts. Yes. No, same. If you apply in parallel, it's going to remain the same. If you apply in series, then they add up. If it's in parallel, it remains the same. If you connect voltage sources in parallel, you can increase the current that is flowing through the circuit. If you increase sources in series, current remains the same, but you can double the volt or you can increase the voltage. For the last case, so it would simply be that would be it. VA and VB are both connected to 5 volts. We can have two independent power supplies powering them. So if that's the case, we can draw it like this, or I can draw it like this. 5 volts, diode D1, and then 5 volts, diode D2. D1, D2, D1, D2. And this circuit can be easily constructed in the lab, right? If you want to apply 0, you just take that wire and connect it to plus 5 volts. And if it's off, you just connect it to either ground or just leave it open. Make sense? So now look at the combination of the input and the output. Create a table. Take a look at the table and tell me what it reminds you of. Absolutely, it's an OR gate. It's a 2-input OR gate. Not recreate, created with just 2 simple diodes. This is, again, as I said, this is something you can easily test it out in a lab. Just put the diodes on the breadboard, apply, just take a 1 kilo ohm resistor, apply 5 volts input to each one of them in turn, and measure the output. Take less than 5 minutes to get that done. But this is how digital logic is implemented in circuits. You can use 2 diodes and create a 2-input OR gate in digital logic. So if you think back to the beginning of this chapter, I said, right, we are using all of these block diagrams for logic gates, for flip-flops, but underneath it all, they're still circuits. They use electric and electronic components. They are just electric circuits underneath. So We apply 0 volts and 5 volts. We represent 0 on paper. In theory, we represent 0 volts as logic 0. We represent 5 volts as logic 1, zeros and ones, or low and high, right? So the voltages would always be either 0 volts or plus 5 volts. Digital logic nowadays is implemented with 3.3 volts, lower power consumption. And so it's possible to do that. Actually, all modern electronics for the last several decades, digital logic always uses 3.3 volts. Okay. But again, that's how it's implemented. Okay. Why specific? It's question being asked, why specifically 3.3? That's the lowest voltage they found that they can create digital logic circuits with appropriate noise margins, because we have to have certain noise margins. So if it's 3.3 volts, you can say anything between 3 and 3.3 volts is logic high. Anything between 0 and 0.3 volts is logic. And I'm just stating like random numbers in that case. But basically, a small top portion is logic high, and a small portion of the bottom is logic 0. So even if the transistor or the diode gives you like 0.2 volts, it is still considered logic 0. And if it's 3 volts, it's still considered logic high. And real life circuits obviously do require 0.6, 0.7 volts to turn on, like diodes and transistors, that forward bias drop. And so we need to account for those voltages also. And then anything that's in the middle is undefined. So anything between like 0.3 and 3 is undefined. We don't, that allows us to keep a gap between the two. Ideally, we would want as small of a voltage as possible. Power consumption. That's the main thing, right? So if let's take the circuit now and flip the diodes. So instead of pointing towards the right, let's make them point towards the left. And instead of connecting to ground, let's connect it to plus 5 volts. And V out is still taken there, the far right. Far left is VB. Okay. Same conditions. Ideal diode. VA and VB can take on 0 volts or 5 volts. Determine VO, all possible combinations. VA and VB. So again, the analysis steps remain the same. Any kind of diode circuit. So what do we see here? Diodes have flipped direction. Input is now being applied to the cathode. Anodes are held at plus 5 volts. So anodes The anodes are held at plus 5 volts through the resistor. Okay. If we wish to find the voltage being applied to the anode, then we need to find the Thevenin equivalent circuit as seen by the diodes. We can just take one diode at a time. But if we find the Thevenin equivalent circuit as seen by the diode, what do we see? One voltage source, one resistor. So Thevenin voltage applied to those diodes is plus 5 volts. Thevenin resistance is resistor R, 1K. So the anodes are always held at plus 5 volts. Okay, always. And that's how we would begin analyzing the circuit. So the anodes are permanently connected to plus 5 volts. Now, if VA is zero, I mean, not A, if the cathode is less than 5 volts, then the diodes are anode is 5 volts, cathode is slightly less than 5 volts. Off, on, on. So if the cathode is 5 volts, it's off. But if it's anything less than 5 volts, it's on. So if VA and VB are 0 and 0 volts, D1 and D2 are both on. If they are both on, what is V out? So I can redraw the circuit like this. Zero volts, meaning where is now D1 is connected there. D2 is connected there. Plus 5 volts, V out. Again, redraw this circuit just to show it like this. V out. So what is V out? Look at the top terminal of V out. It's going towards the left, coming down, going towards the right. It's all one single node. Is the exact same node. So you're measuring voltage at the exact same node. V out is equal to 0. So therefore, V out is equal to 0 volts. If you take a look at the image on the, I mean, not image, the drawing on the left, you can see V out is directly connected to ground. So you're measuring ground basically, or the reference point. So V out is equal to 0. So if that's the case, then we can analyze for other combinations and we can see if either one of VA or VB is 0 or 0 volts, it's connected to ground. So VO is ground. I mean, VO is 0, right? If even a single one of those two diodes is on and connected to ground, then VO will always be 0. So if VA and VB is 0 volts and 5 volts, or 5 volts and 0 volts, here D1 will be off. Sorry, D1 will be on and D2 will be off. And here, excuse me, D1 will be off and D2 will be on. For both combinations, VO is equal to 0 volts, VO is equal to 0 volts. If any single one of those diodes is on, it provides a direct path to ground. And so V0 will always be 0 volts. Let's take a pause, think over that. Let me know if you have any questions. Does that make sense? Yes? No? Any questions? Okay. How about when both inputs are connected to 5 volts? What is the state for D1 and D2? The anodes are connected to plus 5 volts. Now the cathodes are also at plus 5 volts. So the diodes are, show of hands for on, show of hands for off. Okay. Off. And if both of them are off, then resistor is directly connected to V out. So V out, is 5 volts. And if I write the combination of the inputs and output, I get, what do I get? V out is 0.0005. What kind of gate is this? It's an AND gate. Take two diodes, different configuration, and you can have an OR gate, you can have an AND gate. Okay. So as simple as that. So again, yes. Limits the resistor's purpose is to limit the current. Without a resistor in any, so resistors are the most fundamental component for any circuit. If you don't have a resistor, that means it's a wire. The resistance of a wire theoretically would be 0 volts. If resistance is 0, doesn't matter how small of a voltage you apply, what is current? V equals IR. I is V divided by R. If R is 0, what is current? Infinite. If R is 0, current will always be infinite. Right? Current will always be infinite. So resistors are a way to limit the current, to actually provide an actual value to the current. Without a resistor in place or without any resistance, current flowing through that wire would be infinite, theoretically. And practically, obviously, that's why we have fuses, right? If you have a short circuit somewhere, short circuit means it's bypassing all the resistors or everything that's in the pathway that could slow down that current or reduce that current. So short circuit simply means you bypassed everything. It's a huge amount of current flowing through. Real life wire will have like maybe a few ohms, not even a few ohms, like less than 1 ohm resistance. So even if you apply like a 1 volt or 2 volts across it, it's going to heat up. And once it heats up, a lot of thermal energy is flowing in a short space in a short period of time, and you have blown fuses. I mean, that's why we have fuse, right? It exceeds the thermal capacity of that filament, and then it just breaks open. That's why in power supplies, we have current limits, we have voltage limits, and we have built-in circuit protection. So if you're ever working in the lab, there's a short circuit in your procedure. I mean, while you are doing it, then the power supply turns itself off. It's built-in circuit potential protection. Well, that's why also batteries are dangerous. So if you have a battery and you short circuit the two terminals of the battery, doesn't matter whether it's a small coin cell, it has some amount of energy, right? But if you short the two terminals of a battery, the resistance is zero between the two positive and negative ends. Apply V equals IR, voltage could be 1.5 volts. R is zero, current is infinite. In a in a power supply unit, there's built-in circuit protection. It senses the short circuit or large current, and it turns itself off. A battery will not turn itself off. And so it'll continuously supply current or releasing all of its energy all at once. Obviously, it doesn't happen all at once, but a large amount of energy is being released, and is being released continuously. So large amount of electrical energy is converted into thermal energy. And that's why we had those exploding phones and exploding battery packs. That's why we can't check in any batteries in flights anymore. They all have to be in the cabin baggage. All right, we'll end class here today, and we'll see you all on Monday. Again, remember, Monday quiz.